So hi, so I think we will start after 3-4 minutes and let's wait for others, and I think we can start at 3-5 p.m. So someone is sharing a screen. Okay, sorry, I have some internet issues. So no worries, you can refer to YouTube videos. Just a moment, just a moment. So I think the Neptel team has shared this link with you, so you can refer to the YouTube videos, and also the lecture material is available. So I think you can refer to week three's material from there. If you still have any doubts regarding that, you can just ask me later after the session, or maybe next time if you haven't watched. So it's 3-5 p.m. So I think we can start. So let me just share my screen. Okay, good afternoon everyone. Just a moment. Good afternoon everyone. So my name is Musaib Rafiq. I'm a PhD student at Electrical Engineering Department at IIT Kanpur. I'm your course TA for this course, Digital Electronic Circuits, that is taught by Professor Gautam Saha from IIT Kharagpur. So today is the fourth live session of this course. We are going to discuss questions, problems related to week 4 lectures, and so instructions are same. So in case of any doubts and queries regarding a particular question, sufficient time will be given after every problem is solved. So you can type in your doubts in your chat box, and also if you are not able to type it in chat box, you can use your microphones. Also, new participants will be added only after a particular problem is solved, so I just have to repeat these instructions every time. So week 4 will cover topics, questions related to multiplexer, demultiplexer, decoder, BCD to 7 segment, decoder driver, encoder, priority encoder, parity generator, and checker. So I think we can begin with our first question. So let me just change the pen first. Yeah. So question number 1, it asks us, consider the output A and B. So we have two outputs A and B with I0, I1, I2 and I3 as inputs and A and B as outputs. So this is given as the Boolean expression of A and B. So the question asks, what is this outbox circuit? So just by looking at the options and looking at the function, we can simply say that is a priority encoder. A priority encoder which has 4 inputs and 2 outputs. So but if we want to solve it completely, we can draw the truth table of a priority encoder. We can create, let me just create a table first, that way it's easy. Insert table 3 4 5 6 6 cross 8. So we can have a truth table like this. So here we have I3, here we have I2, here we have I1, and here we have I0, here we have outputs A and B. So first we will write the and then we'll fill this one. So I just wanted to show you the complete thing, otherwise you can just figure out just by looking at the options only, but let me just show you the complete solution. Oh, so this is 1 2 3 4 1 2 3 4, this should be 0 0 0, and what is happening? How many rows should I fill? 1 2 3 4 5 6 7 8 1 2 3 4 5 6 7 8. I think I need to fill 1 2 3 4 0 1 0 1 0 1 0. 8. So I need to insert one more row. Yeah, now it's fine. So now we, for a 4 cross true parity encoder, when all the inputs are 0 0, we have this output, we don't care about them. So now I0 is 1, so we have 0 1 at the output. Now when I1 is 1, we have 0 0 at the output. When I1 is 1, we have 0 1 at the output. When I1 and when I1 is again 1, so we'll have 0 1 again. Now I2, so we will have 1 0. I2 is 1, so we'll have 1 0. I2 is 1, so we will have 1 0. It should be 4 times. 1 1, then it is 0 0. Yeah, 0 0 1 1, something is 0 0 0 0. Yeah, now 1 1 2 3 4 1 2 3 4. I2 is 1, I2 is 1. Now I3 is 1, so it will be 1 1, it will be 1 1, and so on up to end. One, two, three, four, five, six, seven, 8. Yeah. Now now we will use the minimization function. We'll minimize the function using a k-map. So we will have a 4 cross 4 k-map for A and B. So here we will have I3 and I2, and here we will have I1 and I0. So it's 0 0 0 1 1 1 1 0. Here it's 0 0 0 1 1 1 and 1 0. Now let me just fill the k map. So this is for 1, so we will have all these min terms as 1. You can refer to the truth table also. So now minimizing it, so I'll just change the ink color. So we can have an octet like this, and we can have another octet like this. So the minimize function for A will be simply, here I2 is constant, so it will be I2, and here I3 is constant, so it will be A is equal to I2 plus I3. Now we will do for B. Now we will minimize B. So I'll do it here. So I'll do it here. Same thing, but here I'm doing it for B. So just filling the boxes from the truth table for B. So I'll get something like this. Then now I'll change the ink color to group them. So I can have an octet for this, and I can have a chord for this. So my B will be equal to I2 complement I1 plus I3. So A is equal to this, B is equal to this, just like this, as was given in question. So when we took this truth table for a poor cost true priority encoder, we got these two values for A and B, which were our outputs, and as a result we can say that the outputs A and B equal to this is simply a priority encoder. So some students want to join. Let me just admit them. Sir, you should teach me that chapter which will be submit on. So you want week 6. So actually we are going week wise, so I can't just jump to week 6 tutorials. So this week I have extra questions, and not like you have in assignments. Somewhere some different, some easy, some difficult. So we can't just jump the lecture. Actually, just like I told you in I think week 2nd, I told you that last time when we doing these lectures for NPTEL, so these due dates and week live sessions were coinciding. So in that way you were able to get an idea regarding that particular week. Now since due date has passed, so I can't just jump ahead and discuss week 6 or week 4, week 5. So I need to discuss week 4 only. This is there is a lag of 1 week, I know that, but this is how it is. I can't help with that. But still these questions they will help you. They are not same as you have in assignment. They are somewhat different, some are along those lines, so it will definitely help you in your exams. So just like I told you, demux, you know that we have select lines and we can construct the output functions like y is equal to s2, s1 and all. But here we know for a priority encoder we have 4 inputs and 2 outputs. So what I did, I constructed a priority encoder truth table, and I minimized the functions outputs a and b, and just like the question, I got my outputs a and b. So that way I just reconfirmed that it is a priority encoder. So as you go on, it will come to you intuitionally that this is a priority encoder. That but to reconfirm this thing, you need to draw the truth table and see what are the functions and how are they minimized, and you can just match with the question. Sir, how are you feeling output A and B? So output A and B, so priority encoder, you have these inputs I3, I2, I1, I0. So whenever this I1 is 1, and so let's say I3 is 1, so you don't care about any other input bit. So if I3 is 1, it means your outputs will be 1 and 1. If I2 is 1 and I3 is 0, so our priority will go to 2 and output will be 1, 0, regardless of whatever the values are there for 1 and 0. So let me just show you here. So here we have this, let me take these 4 rows so you can get an idea. So here what we have I1 as 1. So whenever I1 is 1 and I2 and I3 are 0, my priority goes to I1. So I'll write 0, 1. 0, 1 means 1. And again my I3 and I2 are 0 and I1 is 1, so my priority goes to I1 and I'll write 0, 1 for output. Now I2 is 1 and I3 is 0, so I2, the priority will go to I2, and these are don't cares, we don't care about them. As I2 is 1, so output will be 1, 0, 2, that is 2. And now whenever these are 1, my output will be 1, 1. That is how it is. This should not be 1, 0. So I hope it was clear. Any other doubts? Kailash, is it clear? Okay, so should I proceed with question number 2? Okay, so let me just discuss question number 2. So question number 2, what we have here is, we have two 4:1 mux connected to each other, and we are required to find the output x, that is here. So before we proceed to the question, let me just draw 4:1 mux here. So 4:1 mux will have how many select lines? Two select lines, that is S1 and S0, and here I'll have inputs. Here I'll have I3, I0, let me just start with 0, I0, I1, I2 and I3, and output will be 1 here. So here y, so y is equal to I0 S1 S0 complement plus I1 S1 complement S0 plus I2 S0 S1 complement plus I3 S0 S1 S0. So this is the function for 4:1 mux. So similarly we have two mux connected here. So let me just take the first one. So and let's whenever we have these kind of questions, try to label individual outputs. So here I will label this output as F1. Let's just label it as F1, and here we have X, let it be X only. So F1, what will F1 be equal to? So you can take this for a reference. So F1 will be equal to I0. In place of S1 and S0 we have A and B. I0 A complement B complement plus I1 A complement B plus I2 A B complement plus I3 A B. Now looking at our input values, I0 and I3 are 0, so this term and this term will not be there in our output. So f1 will be equal to, and I1 and I2 are 1, so f1 will be equal to a or a and a complement b, or with a b complement. So if you quickly look, if you quickly examine this, this is an XOR gate. Now term it as f1. Okay, now we'll write an output function for let me just separate this thing. So let me just use new page, that will be helpful. New slide. So we'll have it here. Slideshow from current slide. So now we have f1. F1 value we got. So now f2. So we'll write. So s1 here is f1. S1 here is f1. So we'll just write the output function x for 4:1 mux 2. So that thing will be equal to I0 f1 complement, and what is the other line? C complement, plus I1 f1 complement C, plus I2 f1 C complement, plus I3 f1 C, right? So I0 and I3 are again 0, so we'll be reduced to f1 complement C plus f1 C complement. So what is f1? XOR gate, A complement B plus A B complement, and we have and with C, then we have f1 A complement B, here it's complement A complement B plus A B complement, and that's and with C. So you know this is an XOR gate, so XOR gate's complement is XNOR gate, so I can simply write it like this: A B plus A complement B complement, and this thing is ANDed with C, and here I will do the AND operation: A complement B C plus A B complement C. Now let's just expand this. So this is A B C plus A complement B complement C plus A complement B C plus A B complement C. So this is our final solution for X. Now let's just check whether this is any option. So A B C is here. A B complement A complement B complement C, A complement B complement C is here. A complement B C is here. A complement B C complement, A complement B C complement. This is C complement, C complement, C complement, C complement. A complement B C complement is here, and A B C complement is here. So option A is our correct answer. So let me just admit some students first, and if you have any doubts, please type it in the chat box. So you have any question, Kailash? You can ask in chat box. Chat box should be sufficient. So this was question number 2. Any doubts in here? So no doubts. Now going forward to question number 3. So question number 3 is number of select lines required to implement 1:n demux is. So we are required to find the number of select lines for 1:n demux. So we know that for m select lines and n output lines, we have this relation. So we have m select lines and n output lines. So we have this relation: m 2 to power m is equal to n. So sometimes if you get confused, just remember we have demux like 1:4. We have demux like 1:4, 1:4 demux. Yeah, 1:4 demux, and we have demux like 1:8 demux. So for that, for 1:4 demux, we need 2 select lines, and we have 4 output lines. So here we have n output lines, so that means we have n output lines. So here n output lines. So the relation, like here we can see, whenever we have n lines, let's say I have n output lines, so the number of select lines that I will be requiring is m is equal to log to the base 2n. So if I have, let's say, a mux of 1:4, here is my one input line, and I have 2 select lines, and I have 4 output lines. So I have this relation 2 to power m, so m is my select lines and n is my output lines. So I can deduce this relation from here, so that implies m is equal to log to the base 2n, log n to the base 2. So this is your answer. This was a pretty simple question. Now going forward to the next question. Question number 4. 5:32 decoder circuit can be implemented with. So we have a 5:32 decoder circuit, and the question asks us is, among the following 4 options, it can be implemented with which option. So we know that a 5:4. Let's just consider 5:4 decoder, 5:32 decoder. First we will have a 2x4 decoder. Here we will have 2 inputs, and our inputs are A, B, C, D, E, A, B, C, D, E. So here we have 2:4 decoder, 2:4, and here we will have 3x8, 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 and here also we will have 3x8, and here I will have 4 outputs, so A, and each output will go to as enable for one of the 3x8 decoders, like this. And I have my, here I'll have 3 outputs, inputs, sorry. This will be C, let us term it as E. This will be E, here, connection here, here, and here. Then we have D, connection here, connection here, here, and here. And then we have C, here, 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 and here. And here we will have outputs from 0 to 7, then 8 to 15, then 16 to 23, then 24 to 21. So how many inputs we have? 1, 2, 3, 4, 5. And how many outputs we got? 32. So a 5:32 decoder was implemented with a 2x4 decoder and 4 3x8 decoders. So option A is the right answer. So haven't you gone through the lectures, Kailash? And you have asked to repeat question 3. Okay, let me just repeat question 3. Let me just repeat question 3 first. So mux, you know mux, we have a mux, we are also termed as serial to converter converter. So we have one input line here, and we have 4 output lines. Y0, Y1, Y2, Y3, and we have 2 select lines, S1 and S0. Based on the combination of these 2 select lines, our output gets passed to one of the output lines. Input gets passed to one of the output lines. If S1 and S0 are 0 0, then this will be high. If S1 is low and S0 is high, it will go to here. If S1 is 1 and S0 is 0, it will go to I2. And if S1 is 1 and S2 is 1, it will go to I3. This is the working of 1 is to 1 cross 4 decoder. So what we have, so if we have m select lines and n output lines, the relation between this in case of a 1 cross and 1 in case of a demux is that n, that number of output lines, is equal to 2 to power m select lines. So if I have, so here I have 4 output lines, so that means I will have 2 select lines. So the select lines will simply be equal to m is equal to, I'm just taking log on the both sides to the base 2, m will be equal to log 2n. That is what it is. So is it clear now? Question 3. So regarding your decoder thing, I think we will come to that part at end, because maybe that will take time, so I need to cover up all the questions first. So what I suggest you is go through the lectures regarding that portion, and that will be helpful. It's not that difficult. So now going forward to question number which was this, 3 is done, 4 is also done. Now question number 5. So question number 5 asks us find the canonical product of some expression. So we need to find the canonical product of some expression for f of abc for the given finger. So a boolean function is implemented using a mux, 4:1 mux. So we have 4 input lines and 2 select lines, and we need to find the canonical POS function. So let me just write the first what f is equal to. Again referring to that 4:1 mux formula or expression, so I can write it as, this is a, no, let me just write it here, I0 BC plus I1 B complement C plus I2 BC complement plus I3 BC. Now we'll fill the values I0, I1, I2, I3 as given in the figure, according to the figure. So I0 is A, so it's A, B complement C complement. Then I1 is A complement C, it's going through NOT gate, so here I1 will be A complement, so it's A complement B complement C. Then I2 is 1, so it will be simply B C complement. Then I3 is 0, so this still will not be there. So now I need to write it in standard min terms form. So I write it in A B C complement plus A complement B complement C. So here I will just use this A plus A complement and B C complement. So it will be equal to A B C complement plus A complement B complement C plus A B C complement plus A complement B C complement. Now this is equal to sum of min terms. So this is this is equal to A B complement, this is 1, this is 2, this is 4, and this is 6. So in sum of product forms it will be equal to summation of 1 to 4 6. But if we need to get it in standard POS form, we will just take like this and we'll just write those terms which are not present here. So we write 0 3 5 7. So in standard POS form it's product of terms 0 3 5 7. So option C will be our correct answer. So any doubts here? I think this type of question was also in your assignment, so I don't think any doubts will be here. So now moving forward to question number, this was 5, now 6, question number 6. So we have two 2:1 multiplexers connected back to back, and we need to find the Boolean expression implemented by the circuit. So what we'll do, again we will just label each outputs. Here we write as F1 and this is F as it is. So first F1 is equal to, so it will be x complement I0 plus x. Why I'm writing x? Because x is given to the select line, x I1. So as y1 is 0, so f1 is simply equal to x complement I0, and at I0 we are giving input y. Now going towards the second 2:1 mux, so f will simply be equal to z complement I0 of this mux plus z I1 of this mux. So z complement I0 is f1, f1 is x complement y, and z times I1 is f1 complement. So f1 complement is x complement y whole complement, right? Now this thing will be equal to x complement y z complement plus z, and now using De Morgan's law, so this will be equal to x plus y complement. So this thing will be equal to x complement y z complement plus xz plus y complement z. So let's just check whether any answer is given in this form. Yeah, so option B is equal to this xz plus y complement z plus x complement yz. So option B is the correct answer to this question. So any questions? Okay. Now going forward to question number 7. So the question number 7 asks us, find the number of 2 cross 1 mux required to implement 16 cross 1 mux. So we need to find the number of 2:1 mux required to implement the 16:1 mux. So whenever we have this 2 raised to power n cross 1 mux, this thing can be implemented by 2 raised to power n minus 1 2:1 muxes. So 16 can be written as 2 to the power 4. So 16 cross 1, n is equal to 4. So that means 2 raised to the power 4 minus 1 number of 2:1 mux. So that is 16 minus 1. That is the number of muxes required to implement 2 cross 1 mux required to implement 16 cross 1 multiplexer is 15. There is another way of doing it. So we have 16 cross 1. So we'll just divide 16 by 2. So that thing will be 8, and we'll bring this 8 here. And then we'll divide this 8 by 2 again, and that is 4. And we'll divide this 4 by 4, 4 by 2, that is 2. And then we have 2 by 2, that is equal to 1. And we'll just add them up. So 8 plus 4 is 12, 12 plus 2 is 14, 14 plus 1 is 15. So 15 2 cross 1 muxes are required to implement 16 cross 1 mux. So option A is the correct answer. Yeah, option A is correct. So now question 7 is done. Now moving forward to question number 8. So I would like to ask this question to you. First I would like to, you guys to do this question, then I will show you the solution. So I think this question should not take more than 5 minutes. So let me just read this question and do this question at your places. So the output of the circuit shown in this figure, we have 3 2:1 mux, and we have here 0 1 1, x is here input, 0 a is here input, and 1. So we need to find the output of this function. So I'll just, it's 3:40, so I'll give you 5 minutes You guys can do it, and then I'll show you the solution. So I see two of you have done it. Whether right or wrong, I don't know. I'll show you afterwards. I'll just wait for 2 more minutes for others to do. Then I'll show you the solution. So I think, Tanu, have you done it? Or so I think all of you have at least tried. So now let me just check the solution and show you the solution. So sorry to say, but option D and C both are incorrect. Now wait. Okay. Now let me go back to presentation. So am I audible? Let me just check whether I unmuted myself. Yeah. So here we have 3 2:1 mux connected back to back. So let me just label each one's output. Let me just label this as F1, this as F2, and output as output, or we can write it as F3. So my F3 is output. So let me just first check F1. F1 will be simply equal to F1, this is I0 and this is I1. So select line is 1, so that means I1 will be selected and I1 is 1, so F1 is 1, right? Now F2 will be equal to, so see, F2 will be equal to, this is I0 and this is I1. Select line is 0, so I0 will be selected and I0 is equal to X, so F2 is equal to X, right? Now F3, which is our output, I1 will be selected. Here A is I0 and this is I1, so F3 will be equal to simply F2, and F2 is equal to X. So option B is the right answer. So is it clear? Okay, sir, I did not consider select line. Oh, no need to be sorry. No need to be sorry. This is a learning experience. In fact, a learning experience for you and myself also. So, but whenever you are dealing with mux, you need to check select lines. Select lines are an important part. So it's because the configuration of select lines only then your input outputs are decided. Outputs are decided. Sorry. And the mother says okay. So this was question number 8. Now I can go to question number 9. Let me just let me just stop presenting. Actually my camera, this picture in picture extension is not working. Let me just try using that. So why is it not coming? There seem to be some issue with the picture in picture. Okay, so X is the output of F1 and input of second mux. Why can't we take like that? So what are you suggesting? So you are suggesting X is the output of F1. X is the output of F1, right? X is the output of F1 and input of second mux. Why can't we take that? I don't get it. So let me just show. Yeah, I know that. I'm not sharing the screen. Actually, this picture in picture thing was not working, so I was just checking out that also. So you are saying, what are you saying? You are suggesting X is the output of first mux. No, X is not output of first mux. 1 is output of first mux. 1. And output of second mux is X, and output of third mux is also X. So as this output of first mux, okay, you got it. Okay. So let me just show it again if there are any doubts. So see, here select line is 1, so it means this will get selected, so that means F1 is equal to 1. So this is 1 and this is X. Here select line is 0, so 0 input will get selected, that is X, so X will be here. And also here select line is 1, so this input line will be selected, so F2 is X, so F3 will also be equal to X. I hope it's clear now. So let me just show the next question. So this question, the following circuit diagram, the propagation delay of the multiplexer. So let's just write the individual delays here. So the propagation delay of mux is 2.5. The propagation delay of NOR is 4, and the propagation delay of inverter is 2, and all of them are in nanoseconds. Don't forget the units. I know this is objective type, but you should never forget the units. So these are all nanoseconds, and all the inputs P, Q, R, S, T and activated at the same time. So we need to find the maximum possible. So we need to find the maximum possible propagation delay in nanoseconds to the output Y. So here you can see what is dictating our output are these select lines. So these are 2:1 mux. So based on the criteria of T, one of the input will be selected. So we will calculate total two propagation delays, and whichever is the worst, by worst which means takes a lot of time, we will report that, and that will be our answer. So when T is equal to 0, so this thing will be selected. So this NOR gate followed by this what's it called, followed by this mux. Yeah, NOR gate followed by this mux, and then we have this mux also. and then we have the finally output. So when t is equal to 0, my t propagation delay will be equal to, so TP of the NOR gate plus TP of the mux, 2:1 mux, and finally the TP of another 2:1 mux. So this thing will be equal to TP of NOR gate is 4, TP of mux is 2.5, and TP of mux is 2.5. So 2.5 plus 2.5 is 5, 5 plus 4 is 9 nanosecond. Now when t is equal to 1, I have first this NOT gate. My TP will be equal to TP of NOT plus TP of mux, and then this will be 0, then TP of NOR, and then TP of mux. So this thing will be equal to TP of NOT is 2, TP of mux is 2.5, TP of NOR is 4, and TP of mux is 2.5. So we have 4 plus 5 is 9, 9 plus 2 is 11 nanoseconds. So among the two, this one is the highest. So the maximum possible propagation delay for this circuit when all of the inputs are applied at the same time is t equal to 11 nanoseconds. So I think this type of question was in your assignment, so I don't think there will be any doubts regarding this. Now moving to next question, and that is question number which one we are discussing? Question number 10. Okay, so question number 10. So here the question asks us, determine the inputs of the given mux. So we need to determine these inputs D0, D1, D2 and D3 of the given multiplexer to make the output Q is equal to XY plus Z, correct, where X is MSB. So these things are when I was doing this course of digital circuits last time, that was a different course, so people used to get confused with this MSB and LSB part. So read it carefully, whatever is given and how the function is given. So where X is MSB and Z is LSB, use X and Y as select lines. So the least use X and Y, X is MSB and Z is LSB. So X and Y, so the most significant bits are used as select lines, and the least significant bit is used as input variable. So we need to determine this input combination for the 4:1 multiplexer. So what function we need to implement? So we need to implement this Q. So that is our output is equal to XY plus Z, and we need to implement using 4x1 mux, where X and Y are our select lines. So let's just convert it into first standard sum of product form. So how we will do it? We'll write it like this: XY Z plus Z complement plus X plus X complement Z. So we'll write it here: X Y Z plus X Y Z complement plus X complement Z plus XZ. Then again adding the Y term, so we have XYZ plus XYZ complement. Then we have X complement Y complement Z plus X complement Y Z. Then we have XY complement Z plus XYZ. So XYZ plus XYZ is simply XYZ. So we can write the reduced form as XYZ plus XYZ complement plus XYZ X complement YZ plus XY complement Z, and then finally X complement Y complement Z. So this is equal to summation of min terms 1, 3, 5, 6 and 7, right? Now what we'll do, we'll just draw a table here. I think it's called implementation table, yeah. And we'll just write down, here I have D complement, here I have D, and here it is D0, D1, D2 and D3. So here I write 0, 1, 2, 3, 4, 5, 6 and 7. So whichever min terms is there is high, we need to encircle it. So 1, 3, 5, 7, 1, 3, 5, 6 and 7. 1, 3, 5, 6, 7. So here this is encircled, so it will be D. Here this is encircled, it will be D. Here this is encircled, it will be D, and this will be 1. So that means the input combination should be like this: D0 should be equal to D, D1 should be equal to D, and D2 should also be equal to D, and finally our D3. Okay, this is Z. Sorry, this is Z. This is Z. Z, 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 and D3 should be equal to 1. So D0 equal to Z, D1 equal to Z, and D2 equal to Z, and D3 equal to 1. So option A is our correct answer. So any doubts in here? Okay, that's fine. Now we are done with this question. This was question 10. Now we have question 11. Okay, so the following multiple switching functions. So here we have three multiple switching functions, f1, f2 and f3 are to be implemented by a single decoder and OR gates. So which of the following is the minimum configuration of the decoder and OR gates that are to be needed? So you can see there are three functions, right? And one of the function is having the terms 10, 11, 12. That means we have four inputs, A, B, C, D. Four inputs are needed. That means a 4:16 decoder will be needed, because four inputs are there and 16 outputs will be there. So a 4:16 decoder will be needed. And since there are three separate functions and these need to be ORed, that means some operation which is performed by OR. So for three separate functions we need three OR gates. So the minimum number of minimum configuration that will be needed is one 4:16 decoder, and for each function a OR gate. So we need a one 4:16 decoder and three OR gates. So option C is the correct answer to this question. Now question 12. So this is again, I would like to you guys to do this first, then I'll show you the solution. It's 4 p.m. So at 4-5 p.m. I'll just ask you for your answers, or you can type before that. So 5 minutes for this question. So the question is, the logic function implemented by the multiplexer circuit is ground implies logic 0. So this is a circuit and you have to find the logic function implemented by this mux circuit. So you have 5 minutes, do it. Yeah, I forgot to ask, was there any doubt in question 11? So yeah, option D is correct. So let me just wait for a couple of minutes, so then I'll show you the solution. So the new participant joined in, so the person can also try this question number 12, then I'll show you the solution. Okay, I can see that all of you have done it, and all of you have done it correctly. So let me just show the solution. So what we have here is we have a 4:1 mux. So let me just write it here. So the general expression for a 4:1 mux is written like this. So we have S0 S1 I0 plus I1 S0 S1, or should I write S1 S0? Yeah, that will be better. I2 S1 S0, and then I3 S1 S0. So what we have here is F is equal to, my select lines are P and Q, right? So it's P bar Q bar and I0, then I1 P bar Q, then I2 PQ bar plus I3 PQ. So what is I0? So this is 0, then it goes to NOT gate, it becomes 1, then it again goes to NOT gate, it becomes 0. So I0 is 0, so this thing will be not there. Then what is I1? It goes from 0 to this goes to high 1, so I1 will be 1. So that means it's P bar Q plus I2 is 1 again, it's PQ bar, and I3 is simply connected to ground, and that will be not there. So this is P bar Q plus PQ bar, and this is simply P XOR Q. So that is option D. Now question number 13. We have this function f of a, b, c, d equal to sum of minterms 0, 1, 5, 6, 8, 10, 12, 15, and we have to implement using 8:1 multiplexer. So here A is my MSB and D is my LSB. So one thing I can have here is that I will use A, B, C as my select lines and D as my input line. So I'll just construct the table. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. I don't know why I constructed this extra box. So this is D bar and this is D. So these are my input lines, I0, I1, I2, I3, I4, I5, I6, and then I7. We'll encircle all those minterms which are high here. So we have 0, so this will be encircled. Let me just show you. So 0, 1, 5, 6, 8, 10, 12 and 15, right? That means my output will be here I0. So this is 1, this is 0, this is D, this is D complement, this is D complement, this is D complement, this is D complement, and this is T. So if I have to construct using a 8 cross 1 mux, so these are my select lines B, A, B and C. This is S2, S1, S0, and these are my input lines here. 4, 5, 6, 7, 8. This is 1, this is 0, this is D, this is D complement, D complement, D complement, D complement, and then D. So this is how you implement this boolean function using a 8:1 multiplexer. There's also another way where you can have this MSB as your input and all other bits as your select lines. So what we do there, so we constructed a so I'll write this A as an input to mux and all other are this select lines. So what we'll do here, so we'll construct an implementation table like this. 0, 1. So for that, here it's a complement and here it's a. For that we have to write it like this: 0, 1, 2, 3, 4, 5, 6, 7. Here it's 8, 9, 10, 11, 12, 13, 14 and 15. And you'll encircle all those bits that are high. So you'll encircle 0, 1, 5, 6, 8, 10, 12 and 15. So my I0, this is my I0, I1, I2, so on up to I7. So this will be 1, this will be a complement, this will be A, this will be 0, this will be A, this will be a complement, this will be a complement again, and this will be A. So this is another way where you can have this A as the, which is the MSB as your input and all the bits as your select lines. Yeah, table will again change. That times usually what we have, we either have this MSB. So what I found this in lectures and we take LSB as our input. So that time it's 0, 1, 2, 3, 4, 5, 6, 7. And when we take MSB as our input, so it is 0, 1, 2, 3, 4, 5, 6, 7. So if we take another bit as input, so table will change accordingly. I think it will be then, if we take C as an input, so it will be 0, 0, 1, 2, 3, 4, 5, 6, 7, like that. But usually that's not the case. So I found in this in material and different books, so there they have written the steps like this: take MSB as your input and construct an implementation table like that, and do it like this. So I think you had written we will solve. So did you try using did you try at your end, or you were just checking the solution? Other than that, are there any doubts regarding this question? So okay, we can proceed. So now question 14. So question 14 is a match the following type. So here we have four options: A, B, C, D. A is data selector, B is serial to parallel conversion, C is BCD to 7 segment conversion, and D is signal to binary conversion. And we have to match it with option B. So data selector is simply a multiplexer. So we have this, which is also known as serial to parallel conversion. We have this No, this is parallel to serial. Serial to parallel conversion is data selector is demux. Sorry, that is parallel to serial. Demux is demux. Yeah, demux is 1:4, and this is serial to parallel. Yeah, serial to parallel is serial to parallel is demux. Serial, so this is serial and this is parallel. So serial to parallel is demux. So serial to parallel conversion is demux. So we can have B3. Data selector. So data selector is simply mux, that is parallel to serial. So we have 4 data lines and we select one of the inputs based on the configuration of select lines. So this is 4:1 mux, and this will be your data selector, and this will also use your parallel to serial conversion. So data selector is A, and that is your mux. A is your mux. Oh, this should be B4. A is your mux. A is your mux. So A3 B4, and signal to binary conversion is simply your encoder, and BCD to 7 segment display is your decoder. So we have the combination like this: A3 B4 C1 and D2. Signal to binary conversion is your encoder. So this is option C. These things are very well taught in your lectures. You can refer to them again. These are just nomenclatures and the workings of these muxes and demuxes and encoders and decoders. Now question 15. So this is an interesting question. Actually, I would like you guys to do it, then I'll show the solution. This is a bit tricky question, but I would like you guys to first do it. Yeah, so do it. So decoder. So decoder, basically here is an example of 3:8 decoder. So if all the inputs are 0 0 0, so output will be D0. This bit will be high. D0 will be high. So I'll just show you the truth table of a decoder first. For Kailash actually wants 3:8. So let me just draw it. So if we have a decoder, we will have input line. So let's just construct a 2x4 decoder. So here we have 2 input lines and enable is high. Let's just consider enable is high for a moment, and we have 4 output lines. So this is A and B. So I'll just draw the truth table like this: A, B, and I'll have 4 output lines. That's I, Y3, Y2, Y1, and Y0. This is Y0, Y1, Y2, and Y3. So if my these are my combinations for A and B. So 0 0 means this bit will be high, all other bits will be 0. So if A and B is 1 and A is 0, that means output will be only in 1. Output will be high for Y1, and simply for this it will be Y2, and for when A and B are both 1, output Y3 will be high. So we are just saying when inputs were 1 1, that is 3, so third bit was active. When inputs was 0, zeroth bit was active. When input was 1, first bit was active. When input was 2, second bit was active. So this is my truth table for a decoder, right? So this was a 2x4 decoder, and enable was high, E is equal to 1. And when E is equal to 0, we don't care anything about anything, so all of the outputs are 0. When E is equal to 0, all the outputs are 0. So this was truth table for 2x4 decoder, and I think you might get an idea about the working of this thing. So let me just show you this question again. It's an interesting question. So here is a 3x8 decoder, and here we have inputs x0, x1, x2, and we have outputs d0 to d7, which are connected by this NOR gate, and we are just required to find the f. So do it. So I think it will take 5 to 6 minutes. So it's 4:17, so up to 4:25 I'll wait, then I'll show you the solution. Yeah, option B is correct. So you guys got the catch. So let me just show the solution. So we have x0, x1, x2 as input, 3 inputs, and we have 8 outputs. So and these among these 8 outputs, 3 are connected to the NOR gate. If it was connected to OR gate, it was a pretty straightforward question, but since it's connected to NOR gate, that was a trick. Other than that, it's a pretty simple question. So we have x2, x1 and x0. So it's connected, d1, d4 and d7 are connected to f. So basically f will be equal to d1 plus d4 plus d7 complement. So f should have, f if it was OR gate, f would have been equal to summation of 0, sorry, summation of 1, 4 and 7. Since it's in a NOR gate, so we'll just take the complement and the complement means it is summation of 0, 2, 3, 5 and 6. So in another way we can explain this. So when d1, d4 and d7, any of these inputs are high, my output will be 0. So for my output to be equal to 1, these should always be equal to 0, and these will always be equal to 0 for these cases, d0, d2, d3, d5 and d6. So my output will be sum of min terms 0, 2, 3, 5 and 6. That was the catch. If it was an OR gate, it would simply have been equal to d1 plus d4 plus d7, but it was an OR gate, so it was a complement of those terms, and we get the summation of terms 0, 2, 3, 4, 5, 6. 0, 2, 3, 5, 6. So now going to the next question, that is question okay. So we have a question: design a 4-bit odd parity generator. So we have a 4-bit odd parity generator using a 4:1 mux and ABI select line. So we have to construct a 4:1. So we have to construct a 4-bit parity generator using a mux 4:1 mux where AB and select lines. So let me just first draw the 4-bit parities truth table. A B C D. No, I should draw it here. It will be slightly big. So this is A, B, A, B, C, D, and this is my F, which is the output for a parity generator. So this is 0, 0, 0. This is 1, 0, 1, 1, 0, 1. This is 0, 0, 1, 1. So 0, 1, 1. This is 0, 0, 0. This is 1, 1, 1, 1. This is 0, 0, 0, 0, 0, 0. Now we'll show other half. 1, 0, 1, 0, 1, 0, 1. This is 0, 0, 1, 1, 0, 1, 1. This is 0, 0, 0, 0, 1, 1, 1 and 1. This is 1, 1, 1, 1, 1, 1, 1 and 1. Let me just separate them to clear out the confusion. Actually, I get confused, that's why I don't want to draw these. So now we have an odd parity generator. So we have odd parity generator. Here the number of ones are even, so we need an odd parity bit. So F1 is 1. So 1 is already there. So here also it's 0. Here we need 1. Here also it's 0. here we need 1. Number of ones were even, so for parity odd parity generator f is 1. Here is also 1, here is 0, so it's 1 0 0 1 0 1 1 0 1 1, and so here it's also 0, here it's 1, here it's 1, here it's 0, here it's 1, here it's again 0, here it's 0, and finally it's 1. So now we have to minimize the function and see how, and A and B are select lines, and constructed using 4x1 multiplexer, and A and B are select lines, and C and D are inputs. So this we can write the construct the function using the K maps. So here are my inputs A, B, which are select lines. So these are select lines, so they will have combination Z0 0 0 1 1 1 and 1 0, and here are my inputs C and D. So this is 0 0 0 1 1 1 1 0. So let me just mark those terms which are 1. So 0 0 0 is 1, 0 0 0 1 is 0, 0 0 1 1 1, so 0 0 1 0 1 1 0 1 0 0 1 0 1. So these are the select lines. So when input select lines are 0 0, so 0 0, when inputs are 0 0, my I0 input line will be selected. So I0 will be equal to, so this term, so this is what is this? This is C complement D complement plus this term CD. So my when in select lines are 0 1, so that is I1 will be selected. So what will be output? So this term, so this is CD complement plus C complement D. Now here, so what should I write here? So I should write here as I3, not I2, because it's 1 1. So I3 will be equal to, again, C complement D complement plus CD, and my I2 will be equal to C D complement plus C complement D. So finally I0 is equal to, this is C complement D complement or with C D. So this is C XNOR with D. What is I1? C D complement C complement D, so that is C XOR with D. So what is I2? Again C XOR with D. And what is I3? I3 is here C XNOR with D. So my options are C I0 C XNOR with D, I2 C XOR with D, I3 also C XOR with I2 also C XOR with D, and I3 C XOR with D. So option A, yeah, option A is the correct answer to this question. Yeah, sir, we see 0 or 1 for odd parity. Yes, number of zeros and 1 for odd parity. So A, B, C, D, when it was 0 0 0, number of ones were even. So for a parity bit generator, odd parity bit generator, we have to add 1. So to get the number of ones equal to odd. Yeah, you have done it right. Now this was question number 16, right? Now we can move forward to question number 17. So I would like you to do this question. This is a pretty straightforward question. It will take more than 3 to 4 minutes. So I will just read the question, then you can try it. So identify the output Y in the following circuit. So here we have 4x1 mux, and A, B is our select line, and C is my what should I say? C is my input, and you need to find the output. Yeah, just write. Yeah, option 1, B. What is it? B. Yeah, B is correct. Let me just show the solution quickly. So we can write y is equal to a complement b complement d0. Then we can write a complement b d1 plus a complement, no, a b complement d2 plus a b d3, right? So a complement b complement d0 is c, so a complement b complement c, and this is a complement b c complement d1 is c complement, then this is a, so this was complement, so this is d2, so this is a b complement, so we can just write it like this: a complement b complement c plus a complement b c complement plus a b complement c plus a b complement c complement. So this is sum of minterms 1 2 4 5. This is 1, this is 2, this is 4, and this is 5. Sum of minterms 1 2 4 5, right? Now question 18. So what should be the value of d0, d1, so on up to d7, so that the minimized output is f of a b plus c? So first just write the standard in SOP terms, so we can just write it like this. This circuit can be written in SOP terms like this: a complement b complement c complement d0 plus a complement b complement c d1 plus a complement b c complement d0 plus a complement b c d3. Then we have plus a b complement c complement d4 plus a b complement c d5 plus a b comp b b, this is b, written b, b c complement d6 plus a b c d7. So this is basically a 8. If you carefully look at this is simply an 8 cross 1 mux, and we have a function, 3 variable function implemented by it. So what we have here, this is a general form, and what is our function? F is equal to a b plus c, so we can write f is equal to a b plus ac, right? Let's just draw the truth table. This is a, this is b, a b c, and this is f. This is 0 0 0 0 1 0 1. 0 1 0 1. This is 1 1 0 0 1 1. This is 0 0 0 1 1 1, and this 1. So this will be 1 when a b is 1 or a c is 1. So a b, so a b, this will be 0, this will be 0, this will be 0, this will be 0 0 1 2 3 4, this will also be 0, this will be 1, this will be 1, this will be 1. So, and then from this, if we carefully look at, compare these two terms, so f is equal to a b complement c plus a b c complement plus a b c. In order to make these two equal, we see d0, d1, d2, d3, d4, they are all equal to 0, and d5, d6 and d7, that is equal to 1. So option D is our right answer. You could have easily done it like this simply. what we could have done it, we have reduced the function ab plus ac, and then we can write it as like this: abc complement plus abc plus abc plus ab complement c, right? So this is equal to, these two terms are common, so this is equal to summation of min terms 5, 6 and 7. This is basically this thing only, but this is what I'm, this is a kind of a I should not call it shortcut, but things you get intuitively with lot of practice and all. 5, 6, 7. So we have summation of midterms 5, 6, 7. So only 5, 6, 7 need to be selected. That means d5, d6, d7 should be 1 and all other should be 0. That's what it is, simply. Question 17 again, to take screenshot. I think it will be available after the lectures. I will make it available and you can see that Google folder link. You have this Google folder link now in the portal, Google folder link that has links of YouTube videos and folders. I will make it available as soon as possible. Even after the lecture, I'll directly upload it to that only. But still, if you want to take screenshot, I can show you. See. So have you taken it? Okay. Now question 19. Yeah, we have time. So do this question. This is easy. It should take not more than 2 minutes. So I'll read it for you. An 8:1 multiplexer is used to implement a logical function y as shown in the figure. The output y as f of a, b, c, d is given by. So you need to find the output of the function. So I'll just wait for 2 minutes. It should not take more than 2 minutes. Okay, let's look at inputs again. Some are zeros, some are D's. So I think you have missed some zeros, I think. So let me just show you. Yeah, option B is correct. Let me just show you. So this is a 3 a2 mux. So y will be equal to a, b, c complement I0 plus a. Write this thing every time. Sometime whenever, when you are doing it first time, second time, third time, try to write everything at first. And then when you get practice with these things, you can write these things on your own quickly. So this is my y, and what is given, I0 is 0, so this term will vanish. So I'll just mark those terms that will not be there. This will not be there. And then I0 is 0, I2 is 0, so this will also not be there. Then I4 is also 0, and then I5 is also 0, and which term is 0 also, and I0, where is this, I0, this is also 0, 7 is also 0. So what we are left with, we are left with a b complement, I1 is D, then we are left with a complement b c d, I3 is D, then we are left with a b c complement I1, I6 is 1. So y will be equal to a b complement c d plus a complement b c d plus a b c complement d complement plus a b c complement d. So this is sum of 1 plus 1 is 3, this is 1 plus, this is 2 plus 1 is 3, this is 4 plus 2 plus 1, this is 7, this is 8 plus 4 12, this is 13. So sum of min terms 3, 7, 12, 13. Now coming to the last question of today's lecture. So simplify the Boolean functions for the customized. So this is an customized priority encoder given in the table below. So we need to find the inputs and outputs, and we need to find the minimized expression for the outputs. So our outputs are y1, y0 and v. So we can just write it here. We'll first write the output expression for y1, and we are using k-maps to simplify the expression. So we have 4 input variables. Here I have enable and d2, and then I have d1 and d0. So this is 0 0, this is 0 1, this is 1 1, and this is 1 0, this is 0 0, this is 0 1, this is 1 1, and this is 1 0. So let's check it for when is y1 1. Y1 is 1 when d2 is 1 and en is 1. When d2 is 1 and en is 1, and we don't care about d1 and d0, so this row will completely be 1, because there is a don't care condition on d1 and d0, so it will always be 1 when these two are 1. When these two are 1, it will always be equal to 1. And then we have y1 is 1 when this is e and d1 is 1 0 and this is 0 1. So here, so now solving it, we can solve it like this and this. So we have y1 is equal to, this will be e and d2 simply, and this pair will give me term en, this is en, this is d1 complement d0. So my reduced expression for y1 will be enable d2 plus d1 complement d0. Now coming for y0, so this is y0. So here again en and d2 same, 0 0 0 1, 1 1 and 1 0. This is 0 0 0 1 1 1 1 0. So y0 is 1 when en is 1, when en is 1, when d2 is 0, when d2 is 0, and when dn is 1. And there is d0 is no, don't here. 1 0 1 0 1 1 0 1. So this will be these two, and it's also 1 for 1 0 0 1. So we can create two pairs like this, and we can write y1 y0 to be equal to en d2 complement d0 plus en d2 complement d1. So finally we have en d2 complement out, and we have d0 plus d1, and finally we have output v. So this is 1, v1 is 1 when let me just first write 0 0 0 1 1 0. This is 1 whenever en and d2 are 1 1. So this row, and we have don't care on these two, and this is also 1 for 1 0 1 0 0 0 1 1 1 1 0 1 1 0 1 here, and there is a don't care on d0. So 1 0 1 and 1 0 1 0, and then we have finally for 1 0 0 1. This is 1 1, sorry, this was 1 0. So this is one chord, this is another chord, and this is another chord. So we'll get the function as v2 is equal to en d2 plus en d0 plus en d1. So this is equal to en d2 plus d1 plus d0. So y1 is equal to enable d2 plus d1 bar d0. y0 is equal to en d2 complement d0 plus d1, and v is equal to d2 plus d1 plus d1 0. So option D is the right answer. Okay, I see you have done this. So this was all for today's lecture. So if there are any doubts, please ask. Otherwise we'll meet next Sunday at same time from 3 p.m. to 5 p.m. and we'll be discussing problems related to FEEC 5 lectures. Okay, you're welcome, Kailash. So I think I should end this lecture if there are no doubts. Okay, so see you next week. Thank you, guys.